Module 5, Lecture B, Nearest Neighbors. By the end of this lecture, you will be able to explain k-nearest neighbors as classification by similarity to known engineering cases, implement distance calculation, neighbor selection, and majority voting manually, and analyze how feature scaling and the choice of k affect classification results. Similarity-based classification. Engineering case similarity. Nearest neighbor classification assigns a new engineering case to the category of the most similar past cases with known outcomes. For example, a bearing with vibration patterns like faulty bearings would likely be classified as faulty, while one matching healthy examples would be classified as healthy. The method relies on measured similarity rather than detailed theory, assuming similar features usually indicate the same class. Nearest neighbor classification works best when every case is described with consistent features, such as measurements from inspections or machine sensors. It classifies a new case by comparing its feature values with known cases and choosing the closest match. This approach is useful in engineering because it can capture complex patterns that simple rules may miss, especially when several measurements interact. Engineering case similarity works only when the chosen features truly distinguish meaningful differences between cases. Superficial matches, such as similar motor dimensions or soil moisture, can hide important factors like thermal stress, grain size, or clay content. Nearest neighbor classification therefore depends on relevant measurements and reliable historical data to make accurate evidence-based decisions. Python code, engineering case similarity. Nearest neighbors compares engineering cases using measured features, then predicts by letting the most similar examples vote. Because similarity depends on feature values, scaling can change which cases count as nearest and therefore affect the result. We import the math library to use mathematical tools like square root for distance calculations. We also import the counter class to count labels and identify the most common one among the nearest neighbors during classification. We define a small data set where each bearing case stores its key features, a name, vibration level, temperature, and a condition label of healthy or faulty. This organized structure makes the cases easy to access and compare for later classification. A new bearing inspection case is created with two features, vibration at 0.3 and temperature at 78. This case can then be compared with existing cases to classify it based on similarity. This distance function compares two cases by measuring how far apart their feature values are after scaling. It normalizes the differences in vibration and temperature using their feature scales, squares those normalized gaps, adds them together, and takes the square root. The result is a scaled Euclidean distance, where smaller values mean the cases are more similar. The function compares a query case with each stored case by calculating a scaled distance, then records each distance with the case's name and label. It sorts these results to find the closest k-neighbors, counts their labels, and chooses the most common label as the prediction. It returns both the predicted label and the nearest neighbors. Two feature scaling choices are defined for comparing cases. One treats vibration and temperature equally by giving both a scale of 1. The other gives vibration a smaller scale and temperature a much larger one, making temperature more influential in distance calculations and potentially changing the final classification. We classify the new bearing case twice, using 3 nearest neighbors. First, we use the classify function without scaling. Then repeat it with scaled values. Comparing the two results shows how scaling can change both the prediction and the nearest neighbor selected. The example introduces a new bearing using its vibration and temperature values, then compares predictions from a 3 nearest neighbors model, with and without feature scaling. In each case, the predicted label comes from the most common label among the 3 closest neighbors, whose labels are shown to explain the decision. The key lesson is that similarity depends on the chosen features and their scaling, so scaling can change which neighbors are considered closest and affect the final prediction. This script uses a nearest neighbors method to classify a new bearing inspection case from vibration and temperature data. It compares results with unscaled features and with scaled features, then uses the 3 closest cases to predict the label by majority vote. Because scaling changes which features influence distance most, the predicted class can change. The main lesson is that feature scaling is important in similarity-based models. Engineering case similarity. In engineering classification, the k-nearest neighbors approach labels a new case by comparing it with similar past examples. If a component resembles ones that were accepted, it is likely classified as acceptable. If it resembles failed ones, it may be judged defective. The method uses the closest known cases as precedent, without requiring complex rules. In engineering classification, a new case is described by features such as temperature, pressure, speed, or material properties, then compared with past labeled cases. If its measurements are closest to cases with a known outcome, it is assigned a similar classification. This works because the method assumes that similar conditions usually lead to similar results. Similarity-based classification uses past examples to judge new cases. Much like engineers draw on experience, its accuracy depends on comparing the right features, because cases that seem similar in one way may differ in important conditions such as temperature, traffic, or weather. In k-nearest neighbors, well-labeled examples act as a reference library, so the method works best when those examples reflect real-world situations. Python code, engineering case similarity. Similarity can be used to classify new engineering cases by comparing their measured features with those of known cases. A nearest neighbors approach does this by measuring distance and using nearby cases to vote on the classification. We import the math library to use mathematical tools needed for Euclidean distance calculations. We also import counter from the collections module to count the nearest neighbor's votes and identify the most common classification label. Historical machine records are stored as a list of cases, where each case contains a machine label, its temperature, its vibration level, and its status. This structure keeps past machine data organized so it can be easily compared with new machine cases. The dataset includes 3 past machine cases used to compare against new readings. Cases C and D have moderately high temperatures and vibration levels and are labeled for inspection, while case E has higher temperature and vibration and is labeled as a failure. These examples help predict a new machine's outcome by finding the most similar historical cases. This historical machine case, labeled F, records a temperature of 110 degrees, vibration of 1.25 millimeters per second, and an outcome of failure. It serves as a past example in a dataset used to compare new machine readings with similar cases and help predict whether a machine is likely to fail. We define an unlabeled machine reading using 2 features: a temperature of 90 degrees and a vibration level of 0.58 millimeters per second. To classify it, we choose 3 nearest historical cases so the new reading will be assigned a class based on the vote of its three closest neighbors. Before comparing a new machine reading with past cases, we first check that the case library has enough entries for the chosen number of neighbors. We also confirm that the new reading has the same two features as the historical data: temperature and vibration. These checks prevent errors and keep the similarity analysis consistent. The function measures how similar a historical machine case is to a new reading using Euclidean distance. It compares their temperature and vibration values, squares the differences, adds them together, and takes the square root. A smaller distance means the two cases are more similar based on these features. The code finds the Euclidean distance between a historical case and a new case using temperature and vibration. It compares the two values for each feature, squares the differences, adds them together, and takes the square root to get the distance in feature space. An empty distance list is used to store how close each historical machine case is to the new case. For each case, the Euclidean distance is calculated from its feature values, then saved along with the case identifier and label. These stored results make it possible to find the most similar cases later. The code ranks all historical cases by their calculated distance from the new case, so the closest ones come first. It then keeps only the chosen number of nearest neighbors and collects their labels. These labels are used to find the most common classification, which helps predict the label for the new case. To predict a new case, we count the labels of its nearest neighbors and choose the label that appears most often. A counter tallies the labels, and the most common result gives the predicted classification. This uses the majority label among nearby past examples as the final prediction. The analysis classifies a new machine reading of 90 degrees Celsius and 0.58 millimeters per second vibration using the nearest neighbors approach. It compares the reading with the most similar historical cases, checks their labels such as normal, inspect, or fail, and uses the most common label as the prediction. This shows how similarity to past machine behavior can guide practical engineering decisions. This script uses a nearest neighbors method to classify a new machine reading from past engineering cases. It compares temperature and vibration values using Euclidean distance, selects the three most similar cases, and predicts the new case's label by majority vote. The output shows the new reading, its closest matches, and the final classification. Engineering case similarity. K nearest neighbors is a classification method that compares a new case with similar cases seen before. In engineering, this can help decide whether a component is acceptable or defective by looking at past components with similar measurements. If most of the closest examples were defective, the new component is likely classified as defective too. The method turns experience-based judgment into a structured, evidence-based process. In engineering, similarity is based on measurable features that describe each case. Examples include crack width and corrosion in bridges, temperature and vibration in machines, or pH and turbidity in water samples. The main idea is that cases with similar features often have similar classifications or require similar decisions, even without fully explaining the physical causes. Similarity-based classification is useful in engineering, but it depends on choosing features that truly capture relevant behavior. Items may look alike on one measurement, such as temperature or moisture, while differing in other important factors like vibration history, density, or grain size. When the selected features are meaningful, k-nearest neighbors can classify new cases effectively. When they are poorly chosen, the results can be misleading. Python code, engineering case similarity. This example compares engineering cases using measured features. Nearest neighbors classification assigns a case based on practical similarity, using manual distance voting to decide which known cases are closest. The code imports the math library to support Euclidean distance calculations, then imports counter to count labels from nearby cases. Together, these tools help identify the most common label among the nearest neighbors. A collection of known motor cases is created to support comparison with new motors. Each case stores a motor's name, temperature, vibration level, and condition label, such as normal. This organized structure makes it easy to review key features and use them in later analysis. Two known motor cases are labeled as failure risks. Motor C with a temperature of 91 degrees Celsius and vibration of 6.8 millimeters per second, and motor D with 88 degrees Celsius and 5.9 millimeters per second. These cases are stored for later comparison with a new motor to assess similarity and possible risk category. A new motor case is represented by two features, a temperature of 84 degrees Celsius and a vibration speed of 5.4 millimeters per second. These values describe the case, so it can be analyzed and compared with known examples. The code validates the data by checking that there are at least 3 known cases and that the new case has exactly 2 features. These checks ensure there is enough data for comparison and that distance calculations can be performed correctly. The function measures how similar 2 engineering cases are by calculating their Euclidean distance. It compares the temperature and vibration differences, squares those gaps, adds them together, and takes the square root. A smaller distance means the cases are more similar in their features. The code finds the Euclidean distance between 2 cases using their temperature and vibration values. It compares each feature, squares the differences, adds them together, and takes the square root. The result shows how far apart the 2 cases are in this 2-dimensional feature space. We create a list to store how far each known motor case is from the new case. For each known case, we use the distance function to compare temperature and vibration, then save the resulting distance along with the case's name and label. This gives a simple measure of how similar each known case is to the new one. The code stores each known motor case's distance from the new case, along with its name and label. This lets the program track which cases are most similar based on the measured features. Later, these stored values can be sorted to choose the nearest neighbors for classification. To find the 3 most similar known motor cases, choose 3 nearest neighbors. Then sort all calculated distances from smallest to largest. The first 3 distances identify the closest cases to the new motor case based on the measured features. To make a prediction, we collect the labels from the nearest neighbors and count how often each one appears. The most frequent label is then chosen as the result. This is the majority vote among the nearest neighbors. We first summarize the new motor case by noting its temperature and vibration levels. Then we introduce the nearest known cases, helping the listener see which past examples are most similar based on the calculated distances. The loop goes through each nearest neighbor and retrieves its distance, motor name, and condition label. It then prints a short summary showing the motor name, the rounded distance to the new case, and the label. This makes it easy to compare how similar each known motor case is to the new one. The code outputs the predicted classification for a new motor case using a majority vote among its nearest neighbors. This shows how the k-nearest neighbors algorithm makes a prediction by comparing the new case with similar past engineering cases. This script demonstrates a basic k-nearest neighbors classifier for motor condition data. It compares a new motor case with known cases using temperature and vibration, calculates Euclidean distance to measure similarity, and selects the 3 closest matches. The new case is classified by majority vote among those neighbors, producing either a normal or failure risk prediction. Manual KNN implementation. Distance calculation. In manual nearest neighbors classification, the first step is to measure the distance between a new case and each known case. Each case is treated as a point described by its feature values. Smaller distances mean the cases are more similar, while larger distances mean they are less similar. At this stage, the goal is simply to rank known examples by similarity, not to make the final classification. When calculating distances by hand, compare the same features in the same order in units for every case. For a new component, find the differences in thickness, weight, and surface roughness, then combine them into one distance value. Smaller distances mean the cases are more similar, while larger distances show greater differences. Feature scaling is important when calculating distances because features with larger numerical ranges can dominate the result. For example, mileage could outweigh engine temperature in vehicle diagnostics, even when temperature matters more. Scaling helps each feature contribute fairly, so distance calculations can more accurately identify nearest neighbors and support class voting. Python code distance calculation. Manual k-nearest neighbors begins by calculating distances between cases. The idea is that similar engineering cases should be close to each other, but the way features are scaled can strongly affect which cases appear most similar. The script first imports the math library to support calculations such as square roots. It then imports pandas, which is used to organize and analyze data in a structured table called a data frame. We create a pandas data frame to organize historical component data. It stores each case identifier, along with thickness, weight, surface roughness, and a label marking the component as acceptable or defective. This structured set of known cases can then be used to compare and evaluate new components. We define an unlabeled component using a dictionary to store its key features: thickness, weight, and roughness. These measurements match the features used for the known cases, so the new component can be compared consistently. This consistent feature set is needed for calculating distances later. We first choose the key features for comparison: thickness, weight, and roughness. Their order sets how the known cases and the new case will be compared. We then confirm that these features exist in the known cases data, which prevents errors when calculating distances. This function prepares to calculate Euclidean distance between a known data point and a new one. For each feature, it finds the difference between the two values, squares that difference, and stores it. These squared differences are then ready to be combined into the final distance calculation. Euclidean distance measures how far apart 2 points are by comparing their corresponding features. It adds the squared differences between those features, then takes the square root of the total. In k-nearest neighbors, this distance helps determine which points are most similar. A new distance column is added to the data frame to measure how far each known case is from the new component. This is done by applying a row-by-row function that uses the Euclidean distance calculation on the selected features. The result gives each case a distance value, which can then be used to compare similarity or sort the cases. Sort the known cases by their distance from the new component from closest to farthest to find the most similar examples. Then keep only the key information, the case identifier, label, and distance. Selecting the first 3 rows gives the 3 nearest known cases for comparison. We first show the new component's features so we know what it is being compared to. Then we display the closest known cases using the manually calculated distances in a clean, readable format. The key idea is that the smallest distance points to the most similar case, because nearby points in feature space are more alike. This script compares a new component with known cases by calculating Euclidean distance using features such as thickness, weight, and roughness. It adds each distance to the dataset, sorts the cases from most to least similar, and reports the 3 nearest examples. The closest case has the smallest distance, making it the most similar. This demonstrates the distance calculation used in k-nearest neighbors, and shows why choosing and scaling features matters. Neighbor selection. After measuring how far a new case is from known cases, the model selects the closest ones to guide its classification. The number of neighbors chosen is set by k, such as 3 nearest cases or 5 nearest cases. This focuses the decision on the local neighborhood based on the idea that nearby cases are more likely to share the same class. Manual neighbor selection means ranking past cases from most to least similar, using their calculated distances, then choosing the closest ones. In a motor vibration example, an engineer would compare a new pattern with the nearest past records to support a normal or faulty decision. This step identifies the most relevant records, but the final classification comes later. Choosing neighbors that are too distant can reduce classification quality. When implementing nearest neighbors by hand, handle ties and duplicate observations consistently, especially when several cases are equally close. The choice of how many neighbors to use is important. A small number captures local patterns but can be sensitive to noise, while a larger number is more stable but may include less similar cases. In soil classification, this means too few neighbors may overreact to local variation, while too many may blur distinct zones. Python code, neighbor selection. Manual k-nearest neighbors works by finding the closest engineering cases, sorting them by distance, and then using the nearest ones to vote. Choosing a small value for k makes the decision depend on a very local neighborhood. The code imports the square root function from Python's math module to calculate Euclidean distance between points. This distance calculation is needed for the k-nearest neighbors algorithm, and importing only the required function keeps the code focused and lightweight. A list is created to store known motor cases for later comparison. Each case includes a name, vibration level, temperature, and a label showing whether the motor is normal or faulty. This structure keeps the key information organized and easy to access in the code. The snippet defines 3 motor examples, each with a name, vibration level, temperature, and condition label. 2 examples, C and D, show higher vibration and temperature and are labeled as false, while example E has lower values and is labeled normal. These records form a small dataset for comparing new motor measurements and judging their condition. A new known motor case is added to the dataset. It is labeled F, has a vibration level of 3.2 and a temperature of 70, and is marked as faulty. This example helps the system compare future motor measurements and predict whether they are normal or faulty. A new motor case is represented by 2 readings, vibration of 2.7 and temperature of 62. These values will be compared with known cases to classify the motor as normal or faulty, based on which cases it is closest to. This check makes sure there are at least 5 known motor cases before analysis continues. If the dataset is too small, it stops with an error saying more cases are needed. The process begins by setting up a place to store distances between the new motor reading and each known case. For each known motor case, the vibration and temperature values are compared with the new case by finding their differences. These differences are then used to calculate the Euclidean distance, which measures how similar each known case is to the new one. The code compares a new motor measurement with each known case by calculating the Euclidean distance using vibration and temperature differences. It squares the differences, adds them, and takes the square root to get one distance value. Each distance is stored with the known case's name and label, so the closest matches can be identified later. The code orders the known cases by their distance from the new measurement, placing the closest ones first. It does this by sorting each case using its distance value. This sorted list is then ready for choosing the nearest neighbors in the next step. We test two neighbor counts, 3 and 5. For each one, we take the closest cases from the sorted distances and use their labels to find the majority class. The code predicts a label by using a majority vote among the nearest neighbors. It counts how many neighbors are normal and how many are fault, then chooses fault only if fault has more votes. Otherwise, it predicts normal. The code gathers the names of the selected neighbors and prints them with the current value of k and the prediction result. This makes it easier to see which cases influence the prediction and what label was assigned to the new motor measurement. To find the closest known case to a new motor measurement, we use the first item in the sorted distance list, since it has the smallest distance. We then report that case's name and its distance, rounded to 2 decimal places. This quickly identifies the most similar known measurement and gives a sense of the new measurement's nearest neighborhood. This script manually applies k-nearest neighbors to classify a new motor case using vibration and temperature data. It measures how close the new case is to each known case, sorts the results, and predicts normal or fault by majority vote among the nearest neighbors. It compares predictions using 3 and 5 neighbors, shows which cases were closest, and reports the single closest case with its distance. Majority voting. In manual k-nearest neighbors classification, majority voting assigns a new case to the class that appears most often among its closest known neighbors. After finding the nearest examples, you simply count their labels and choose the most common one. This makes the method easy to apply by hand because it depends on label counts rather than a learned formula. In majority voting, the classification is based only on the labels of the selected nearest neighbors, so counting them accurately is essential. After finding the closest examples, record their labels and choose the class that appears most often. For example, if most of the nearest components are acceptable, the new component is classified as acceptable. This same idea applies in many settings, such as soil classification or support ticket categorization. When using majority voting manually, plan how to handle ties or very close votes before making predictions. Common choices include using the class of the nearest tied neighbor or giving closer neighbors more weight. These rules matter because they can change the final classification when the evidence is mixed. So majority voting should be treated as a consistent decision rule shaped by the data context. Python code. Majority voting. Manual KNN voting classifies a machine condition by looking at nearby labeled cases. The predicted class is the one with the highest count among those neighbors. The code imports tools needed for a nearest neighbor classifier. The counter class is used to count the labels of nearby cases, while the math module helps calculate Euclidean distances to measure how close known data points are to a new case. The data is organized as a list of machine condition cases. Each case includes two measured features, vibration and temperature, along with a label such as normal, bearing fault, or overheating. This structure makes the data easy to use for later analysis, including machine learning classification. The dataset contains 3 example machine conditions described by vibration and temperature. 2 examples with high vibration and moderate temperature are labeled as bearing faults, while one with lower vibration and higher temperature is labeled as overheating. These known cases can be used to classify new machine conditions by comparing how close they are to the examples. A new case is added to the classification list with 2 features, a vibration level of 3.2 and a temperature of 88. Its label is overheating. This case can then be used with the other stored cases in a majority voting algorithm. We define a new unknown case with vibration at 2.7 and temperature at 40. Using k nearest neighbors with k set to 3, we compare it to the 3 closest known cases to help decide its class. The code first checks that k is a valid choice for the dataset. It must be at least 1 and no larger than the number of available cases, since it represents how many nearest neighbors will be used. If k falls outside this range, the code raises an error, so the value can be corrected before running the k nearest neighbors algorithm. The process compares a new case with each known case in the dataset using vibration and temperature. For each known case, it calculates the Euclidean distance to the new case, then stores that distance with the case's label. These distances show how similar each known case is to the new one. The code stores each known case's distance from the new case, together with its label. This lets the k nearest neighbors algorithm sort the cases by distance and choose the closest labeled examples for classification. The code orders the distance and label pairs from closest to farthest, then keeps only the first k cases as the nearest neighbors. These neighbors are then used to decide which label is most common among the closest examples. To make a prediction, we count the class labels among the nearest neighbors and find which label appears most often. The most frequent label becomes the predicted class because it represents the majority vote of the closest cases. We review the nearest neighbors by showing their class labels, then count how often each class appears. The predicted class is the one with the most votes, making it the most likely classification for the new case. We also report the winning vote count and compare it with the total number of neighbors considered. This script uses k nearest neighbors to classify a machine's condition from vibration and temperature data. It compares a new case with vibration 2.7 and temperature 40 to labeled examples using Euclidean distance, then looks at the 3 closest cases. The predicted condition is chosen by majority vote among those neighbors, and the output reports the neighbor labels, vote counts, final class, and majority size. KNN behavior. Feature scaling. Feature scaling is important in k nearest neighbors because the model compares cases using distance. If one feature has a much larger numerical range, it can dominate the distance calculation even when it is not more meaningful. Scaling puts features on a fairer basis, so the idea of which cases are near each other reflects the problem rather than the units of measurement. Feature scaling changes how distance-based models like k-nearest neighbors compare cases. If one feature uses much larger numbers than another, it can dominate the distance calculation and distort predictions. Scaling puts features on a more comparable footing, so similarity reflects the overall pattern rather than just the largest measurement scale. This can affect classification in areas such as medicine, finance, and manufacturing without adding new information. Feature scaling is essential in k-nearest neighbors because the algorithm compares raw distances and does not account for different measurement units. Without scaling, features with larger ranges can dominate the distance calculation and lead to misleading neighbor choices and predictions. Scaling should be fit on the training data and applied consistently to new data, and analysts often compare performance before and after scaling to see its effect. Python code. Feature scaling. K-nearest neighbors is highly affected by the scale of each feature. This example compares neighbor choices before and after scaling, then uses them to manually classify a new mechanical component. The script begins by importing key libraries, math for standard mathematical functions, NumPy for efficient numerical work with arrays, and matplotlib's plotting tools for visualizing data and results. We store mechanical component data in a two-dimensional NumPy array, where each component is described by surface roughness and operating temperature. Roughness is measured in micrometers, and temperature in degrees Celsius. This structure makes the data easy to analyze and manipulate with NumPy array operations. We store each mechanical component's quality label in a NumPy array, marking it as acceptable or defective. These labels will later help classify a new component by comparing it with its nearest neighbors in the dataset. We define a new component to classify using two features: a roughness of 4.4 micrometers and a temperature of 760 degrees Celsius. The k-nearest neighbors method will use 3 nearest neighbors. This setup lets us compare how the classification changes when feature scaling is applied versus when it is not. We first check that the component data has the expected structure: 6 components, each with 2 features. We also confirm that the number of quality labels matches the number of components. These checks help prevent dimension mismatches that could cause errors during later classification steps. We calculate the unscaled Euclidean distance from each component to the new part by comparing their feature values in the original feature space. For each component, the feature differences are squared, added together, and then square-rooted to give a single distance value. This shows how far each component is from the new part before any scaling is applied. To scale the features, we first find the minimum value of each feature across all components. Then we find each feature's range by comparing its maximum and minimum values. These ranges let us put all features on a common scale, so each one has a fair influence on distance calculations in the k-nearest neighbors algorithm. To avoid division by 0 during scaling, 0 ranges are replaced with 1 using NumPy's where function. Each feature is then normalized by subtracting its minimum value and dividing by its range, placing values between 0 and 1. This helps features contribute more evenly to distance-based methods such as k-nearest neighbors. Scale the new component the same way as the training data by subtracting each feature's minimum value and dividing by its range. Then compare it with the scaled components using Euclidean distance, which measures the overall difference across all features. These scaled distances allow the k-nearest neighbors algorithm to make fair and accurate comparisons. This function performs the voting step in k-nearest neighbors classification. It finds the closest k-neighbors by sorting distances, gathers their labels, counts how often each label appears, and returns the most frequent label along with the selected labels. In short, it classifies a point by choosing the label most common among its nearest neighbors. We use the k-nearest neighbors method to classify a new component with k set to 3. First, the vote is based on raw distances, then the same process is repeated using scaled distances. Comparing the two results shows how scaling can change which neighbors are closest and may affect the final predicted class. This section compares k-nearest neighbors' predictions for a new mechanical component using roughness and temperature. It first shows the nearest neighbor labels and prediction from the raw, unscaled data, then repeats the process after feature scaling. The key point is that scaling changes how much each feature influences distance, which can change the nearest neighbors and the final prediction. To visualize the scaled neighborhood, we plot the scaled components in a scatter plot. The horizontal axis shows scaled surface roughness, and the vertical axis shows scaled operating temperature. Points are colored by label, with blue for acceptable components and red for defective ones, making the two groups easy to compare. Matplotlib is used to highlight the new component on the plot by placing a black X at its scaled position. The point is based on the scaled surface roughness and operating temperature values, and the axes are labeled to show these two dimensions clearly. The plot is labeled to show k nearest neighbors after feature scaling, making its purpose clear. A lightly transparent grid is added to help interpret the data point positions, and the plot is then displayed to show how scaling affects the KNN classification results. This example shows why feature scaling matters in k-nearest neighbors classification. A small dataset of mechanical components is classified using roughness and temperature, first with raw values and then after min-max scaling. Because unscaled features can dominate distance calculations, scaling changes which points are nearest and may change the predicted label. The key lesson is that distance-based methods need features on comparable scales to produce meaningful results. Feature scaling. In k-nearest neighbors, feature scaling matters because the model relies on distances between data points. Features with larger numeric ranges can dominate those distances, even when they are not more important. Scaling puts features on a comparable basis, so the idea of which points are near each other reflects the problem rather than the units of measurement. Feature scaling makes different measurements comparable so distance-based models are not misled by large numeric ranges. Without scaling, a feature measured in thousands can dominate one measured in small units, even if both matter, as in medical triage or manufacturing data. Scaling does not add information. It adjusts the geometry of the feature space, which is especially important for k-nearest neighbors because it depends directly on distance calculations. Feature scaling helps k-nearest neighbors classification by preventing features with large numeric ranges from dominating distance calculations. After scaling, all features can influence neighbor selection more fairly, which may improve results. However, scaling does not fix irrelevant features, so analysts should still choose features carefully and compare results before and after scaling to check that the neighbors make sense. Python code. Feature scaling. K-nearest neighbors is highly affected by the scale of each feature. This example compares neighbors found with raw data versus scaled data, using a small engineering dataset to keep the calculations easy to follow. We import three key libraries: Math for basic mathematical functions and constants, NumPy for efficient numerical work with arrays, and Matplotlib PyPlot for creating plots to visualize data. The data is organized into separate NumPy arrays for component roughness, operating temperature, and quality labels. Roughness is measured in micrometers, temperature in Celsius, and each label marks a component as acceptable or defective. This structure makes the data easy to manage for later tasks, such as scaling features or building a classifier. We define a new component to classify using its roughness and temperature values, 3.6 and 650. The existing roughness and temperature data are then combined into a two-column feature matrix, where each row represents one component. An assertion checks that the matrix has 6 rows and 2 columns, confirming the data is correctly structured for the next processing step. This function measures how far a new case is from each point in a dataset using Euclidean distance. It compares each feature, squares the differences, adds them for each data point, and takes the square root. The resulting distances show how similar each data point is to the new case. The k-nearest neighbors voting function classifies a new data point by comparing it with the dataset, finding the k closest points, and checking their labels. It then chooses the label that appears most often among those neighbors, and returns that label along with the neighbor indices. To standardize the data, we find the average and standard deviation of each feature across all data points. Then each feature value is adjusted by subtracting its average and dividing by its standard deviation. This gives every feature a mean of 0 and a standard deviation of 1, which helps scale-sensitive algorithms like k-nearest neighbors work more reliably. To classify a new case with k-nearest neighbors, we compare results using both raw and scaled features. Scaling uses the training data's mean and standard deviation so the new case matches the training scale. We then find the 3 nearest neighbors and use their most common label as the prediction. Comparing the raw and scaled predictions shows how feature scaling can change the nearest neighbors and the final classification. The code compares k-nearest neighbors classification with and without feature scaling, using k equals 3. It first shows the prediction and nearest neighbor labels in the raw feature space, then repeats the same checks after scaling. This highlights how scaling can change which neighbors are selected and, as a result, the final classification. Each data point is colored by its label. Acceptable points are blue and all others are red, using NumPy's where function. A matplotlib figure is then created and roughness is plotted against temperature as a scatter plot. The points are made larger to improve visibility. The plot highlights the new case with a large black X marker at its coordinates, making it easy to distinguish from the other points. The axes are labeled with surface roughness in micrometers and operating temperature in Celsius. The title emphasizes the key lesson. When using k-nearest neighbors, raw feature units can dominate distance calculations, so scaling matters. To add a legend manually, create invisible scatter points that represent each category. Use blue for acceptable cases, red for defective cases, and a black X marker for the new case. These hidden points define the legend entries, and the legend function then displays them in the best available location on the plot. The layout adjustment makes the plot easier to read by preventing elements from overlapping. The display command then renders the visualization, so we can view the data and the new component in the feature space. This script shows why feature scaling matters in k-nearest neighbors classification. It compares distance calculations for a new component using raw measurements and standardized features, then predicts its quality label from the 3 nearest neighbors. Because k-nearest neighbors depends directly on distance, features with larger numeric ranges can dominate the result if they are not scaled. The example demonstrates that scaling can change the predicted class and uses a plot to illustrate how the raw feature space affects the distance-based decision. Choosing k. Choosing the number of neighbors in a nearest neighbors classifier controls how specific or general its predictions are. A very small number makes the model rely heavily on the closest examples, which can capture fine details but also makes it sensitive to outliers, errors, or unusual cases. This can lead to unstable predictions, such as when a machine failure estimate is influenced by a faulty sensor reading. Increasing the number of neighbors in a nearest neighbors classifier makes predictions smoother and less sensitive to noisy data, because the model relies on the most common class among more nearby cases. But if the number is too large, it may include irrelevant points and become too general. In that case, the model can miss important local patterns and favor the dataset's dominant class instead. Choosing K in a nearest neighbors classifier means balancing sensitivity to nearby examples with stability against noise. The best value is usually found by testing several options on validation data, not by relying only on training performance. Smaller values work better for large, clean datasets with clear class separation, while larger values can be more reliable when the data is noisy. In two-class problems, an odd value is often used to reduce ties. Python code. Choosing K. This section explores how changing K affects K nearest neighbors. Using small engineering measurements, it shows how a low K can make predictions more sensitive to local data, while a higher K produces smoother voting across nearby points. The script imports three tools needed for a K nearest neighbors workflow. The math library supports distance calculations. Matplotlib/pyplot helps visualize data, and counter from collections counts class votes when predicting a new data point. A collection of engineering measurements is stored as records, where each record includes vibration amplitude, temperature, and a condition label, such as normal or fail. This structure keeps the data organized so it can be used to analyze patterns and predict the condition of new measurements. The dataset includes three failed component cases, each described by vibration amplitude and temperature. The values range from 2.8 to 3.2 for vibration and 78 to 82 degrees for temperature. These examples are used to study how different choices of K influence the behavior of the K nearest neighbors algorithm. A new failure data point is added with vibration amplitude 1.55 and temperature 64 degrees. Because it lies near the boundary between normal and failure cases, it adds noise that helps test how sensitive the K nearest neighbors model is to small changes in the data. A new component measurement is defined using two values, vibration amplitude of 1.5 inches per second and temperature of 64 degrees Celsius. This measurement will later be used by the K nearest neighbors algorithm to predict the component's condition. Before analysis, the code checks that the data is valid and consistent. It confirms there are at least three cases, which is the minimum needed to identify useful patterns, and that the new measurement contains exactly two values, vibration and temperature. These checks ensure the data is ready for further processing. The distance function measures how far apart two points are using their vibration and temperature values. It compares the two values for each feature, then combines those differences using the Euclidean distance formula. The result is a single distance value that represents separation in two-dimensional space. The function creates a list to store each existing case's distance from the new component, along with its label. It then goes through the dataset, compares the new vibration and temperature measurements to each case using Euclidean distance, and saves the result. These stored distances prepare the data for finding the nearest neighbors. The code predicts a label by finding the closest measurements, keeping the chosen number of nearest neighbors, and counting their labels. It then selects the most common label as the prediction, and also returns the full vote count for review. We test several odd values for K to see how the number of nearest neighbors changes the K nearest neighbors prediction. For each value, The prediction function estimates the label of the new measurement using the closest data points. The results are collected, so we can compare the predicted labels and voting details for each choice of k. The output introduces the k-nearest neighbors predictions for a new component and compares results across different values of k. For each k, it reports the predicted class and the vote distribution among classes. This shows both the final prediction and how strongly the neighboring votes support it. The data is split into two groups based on its label: normal cases and failing cases. For each group, the vibration and temperature values are extracted and stored as paired points. These grouped points can then be used to plot the data and visually compare normal behavior with failures. We create a 6 by 4 inch plot to visualize the data clearly. Then we add two scatter plots, one for normal cases and one for fail cases, using vibration and temperature as the plotted values. Both groups use the same point size, so the comparison is consistent and easy to read. Matplotlib is used to highlight the new component on the plot with a large star marker at vibration 1.5 and temperature 64. The point is labeled as the new case, so it appears clearly in the legend. The axes are also labeled to show vibration amplitude in inches per second and temperature in degrees Celsius, making the plot easier to interpret. The plot is prepared to show how different values of k affect k-nearest neighbors classification, from more locally sensitive decisions to smoother voting. A legend identifies the existing classes and the new component, while a subtle grid improves readability. Displaying the plot lets us compare how each k value changes the new component's classification based on nearby data points. This script demonstrates how the choice of k changes predictions in the k-nearest neighbors algorithm. It compares a new engineering component with labeled examples using Euclidean distance, then predicts normal or fail by majority vote among the nearest neighbors. Smaller k values make the result more sensitive to nearby points, while larger values produce smoother, more stable voting. The printed results and plot show how different k values affect the classification and decision boundary. In this lecture, you learned to explain k-nearest neighbors as classification by similarity to known engineering cases, implement distance calculation, neighbor selection, and majority voting manually, and analyze how feature scaling and the choice of k affect classification results. In the next module, Module 6, we will go over none. Thank you for your attention. See you all in the next lecture.